Okay, done or not done, let's correct these two questions. So last night for homework, you had two questions from section 5.3 on adding and subtracting polynomials. The question asks you to both model and solve numerically. So the first thing I'm going to do is I'm going to draw it. And when I draw 2x, I represent it with x tiles. Now remember, an x tile is called an x tile because its length is x and its width is 1, and therefore its area is x. When we talk about x square tiles, we're talking about these bigger ones. And the reason why they're called x squared is because the length is x, the width is 1, and the area would therefore be x times x, which we know from our unit exponents is x squared. So we're going to start with drawing two x's and a negative 4. Now you can use those little square ones because that's supposed to represent the opposite of 1 times 1, right? The area, the empty one. But because integers are a part of what we've already learned, we'll just represent integer chips for now in terms of these polynomials with just -1 integer chips. When I combine that with a negative 3x, remember the negative 3x means the opposite of x. So if this is x, this is the opposite of whatever number that is, right? The opposite of x, or the negative version of that number. And then negative 4 over here. Since we're adding them, we're really combining them. And two of these and two of these will make an algebraic zero pair, leaving me, and I'll write it up top, I guess. Might be best to do it up here. Leaving me with just this one here, which is a negative 1x. Keep in mind we don't need the coefficient of 1. We understand that that's negative 1x, but we just write negative x. And these 4 and these 4 do not combine to make zero pairs. There's just -8 of them. So my constant will be -8, and therefore, when that binomial is added to this binomial, the solution will be negative x minus 8. When we solve it numerically, we don't actually draw it, but we do the same thing. We identify like terms when we're adding. In this case, I identify x's. I identify the x's over here. And when I combine those like terms, what do I really combine? The coefficients. I keep the term, in this case, I keep the x, and I combine the coefficient of 2 with the coefficient of -3, and I end up with -1, which we're just going to write like that, right? -1x. A -4 combines with a -4 to make a -8, and therefore I get the same solution, but I don't need to draw it to get my answer. In the second question, we have subtraction. Now, because it's subtraction, when we model it, what you need to start with is just a space. Just start with a space. And in that space, I want you to draw your first term. So x squared, -2x, and +3. Now, from this trinomial, I need to subtract this trinomial. Or I have to remove from that trinomial that second trinomial. So it asks me to subtract -2x squared. Looking in that particular square, do I have -2x squareds to remove? No. So what we talked about was, in order to have that without affecting what's in there, if I think about this, that's an x squared and a -x squared. The value of that, Avery, is what? This right here. What's the value of that? 0. So I'm going to infinite clone this because I'm going to make my life a little bit easier. So if I add that to this particular square, have I changed the value of that interior? No, I haven't. It's still the same thing it was because I added nothing to it. And likewise, when I do that, I still have not changed x squared minus 2x plus 3. It's still that same value, whatever that happens to be. But in doing so, I now have, excuse me, -2x squareds that I can remove. Okay? Do I have 5 negative x's to remove from there? No, I don't. So if I then take about the same idea, there's my zero pair of algebra with x's, infinite clone it, infinite clone. Adding that does not change the value. Adding that does not change the value. Adding that does not change the value. But in doing so, I now have 1, 2, 3, 4, 5. That's the worst drawing around there I've ever seen. I can remove 5 negative x's. That's awful. That is really awful. Without affecting it. And finally, can I remove 3 positives? Yes, I can. I don't need to add anything to that because I do have 3 positives that I can remove, don't I? Now my drawing is chaotic. I apologize. But these 5 negatives, I'm just going to scratch them out because those are all gone, correct? I remove them. What we end up with is 1, 2, 3 x squareds. We end up with 1, 2, 3 x's. And we end up with no constant. Is that right? So we end up with 3x squareds left and positive 3x. And that's a little chaotic. I'm not going to lie to you, that's a little chaotic. However, it's much easier to do this question. It's much easier to do this question if we use the idea of what? Without modeling it, what's the easiest way to subtract polynomials? We're going to use that same integer thing. So back in grade 7, you learned that the easiest way to do this was to think of it as being -2 plus the opposite of -3, which is this, right? We learned KFC. KFC still works for polynomials as well as integers. So if I keep this first polynomial as is, change subtraction to addition, and instead of using this polynomial, I'm going to use the opposite of every term in there. That's what I'm going to use instead. So I'm going to add the opposite. So I'll erase this. I'll bring this up. And that should be the same answer, correct? And the reason why this is easier, because now all I'm doing is gathering like terms. X squared plus 2x squared is 3x squared. Negative 2x and positive 5x is positive 3x. And positive 3 and negative 3 make nothing. And I end up with the same answer I got with modeling, but I use gathering like terms.